So exponential functions are power functions. And a power function just means there is a base and there is an exponent, right? So for example, if I have, like until now, right, our functions look like this, x to the power of 3, and so on. So we had a base and an exponent, and the base was a variable, and the exponent was a constant, okay? Right now, we're going to switch things up. We're going to switch it to a constant as a base and a variable as an exponent. This is an exponential function. So it's a power, okay? A power is anytime you've got a base and an exponent, but the base is the constant and the exponent is a variable. All right. The two very, very important characteristics of an exponential function is they have asymptotes and they increase or decrease very, very rapidly. All right? So, take a look at some examples of exponential functions here. This one, right? 3 to the x, a constant to the power of a variable. Half to the x, right? A half is a number to the power of a variable. And then here we have e, which is also a number, right? Like 2.7 to the power of a variable. Okay? Jenna, can you fix your math? All right. So, what is not an exponential function is like something like this where you have, for example, 5 to the power of pi and so on, right? Okay, let's talk about some properties of exponential functions. Unfortunately, the best example for this is something like the flu, okay? And I know we're all like going through it right now, but so suppose, right, you come to school one morning and you're feeling just great, but your friend maybe is not and you don't know about it, right? So, just like you always do, right? You come in here Monday morning and you start, oh my gosh, I haven't seen you for like 2 days, right? And like you're all hugging each other and so on and so forth. And, your friend's like, yeah. And like, they're coughing and so on. And, so you were feeling fine, right? But your friend may have had the flu or something like that. And suppose while you were talking with them, just a couple of bacteria landed on you, just a couple, right? And you're like, okay, fine, okay, I'll see you later. And then so by lunchtime, you're like, oh, like, I don't know, like something, right? And then you go home and you just feel weak and, you barely want to move, right? By like 6 or 7, you're in bed, you are just wiped out, okay? And the next morning, like, you can't even get out of bed. So what happened? That morning when you were in school, you had little to no bacteria in your body, all right? A few droplets may have fallen on you, and then very, very rapidly, you went from feeling totally fine to not at all, right? And the bacteria went from little to nothing to like millions and billions, right? In a very short amount of time. That is exponential growth, okay? It happens that quickly. So the idea behind exponential growth is, look, this is one x value, this is the y value. Now if I go to another x value really close by, look at how much higher the y value is. Huh? So, okay? So that's exponential growth, okay? Now, another very important fact about exponential growth is they all have a horizontal asymptote. The default is that y equals 0. Okay. Now, let's talk about two very, very important things. Domain for all exponential functions is negative to positive infinity. That's a free point for you on the test or a quiz. What's the domain of all exponential functions? Negative to positive. You don't even have to think about it. There is no other situation. The range is tied to the asymptote. It's either going to be starting at the asymptote going up or below and ending at the asymptote. So either 0 to infinity and infinity to 0, but it is tied to the asymptote. Okay? All right. That's what I want to talk about right now. So this is exponential growth. Now, back to this idea of you having the flu. Suppose you go to the doctor takes a look at you, they do a swab test and they're like, yep, it's, strep throat or something, right? And they're like, okay, here's a bottle of antibiotics, right? So you start taking the antibiotics and all of a sudden you take one, you take two, and you're like, oh my God, I'm feeling so much better. Because just as quickly as the bacteria may have multiplied, they are now dying out. That is exponential decay. And it works in the same way where a very small amount in the x creates a very big change in the y. What's the domain of exponential decay? All real numbers. And the range is the same idea. It depends on the asymptote. The default asymptote is y equals 0, and the range is connected to that asymptote. Okay, now, one very, very important thing. As you move to the right-hand side, okay, when x's are increasing bigger and bigger and bigger, right? For exponential growth, the graph goes away from the x-axis. So, moves away from x-axis. And it could be either above or below. That's exponential growth. Exponential decay, as you move further and further to the right, the graph moves toward the x-axis or the asymptote. Moves toward x-axis or asymptote. And this is only as you go from left to right. Okay? So as you move left to right. Okay? All right, that's important. So that's how, when you look at a graph, you can figure out, is it exponential growth or decay? But what if you only have a function? How do you figure it out? Well, here's how. This is how an exponential function looks. It's a number to the power of x. It's called exponential growth if b is greater than 1. Okay, what's b? It's the number raised to the exponent. All right? It's exponential decay if that number b is between 0 and 1. So, to do this, you first have to identify the variable exponent. Then you ask yourself, who does that exponent belong to? The 3, correct? Since that number is bigger than 1, it's growth. Okay, so let's do a couple of examples. What do you think the first one is, growth or decay? Growth. How about the second one? B? So who does x belong to? 0.5, which is between 0 and 1. So decay. How about C? Decay. X belongs to 1/3, which is between 0 and 1. Decay. What about the last one? Okay, so it's like it could go either way, right? So let's see. Okay, so let's see. Here's the exponent. It belongs to the 1/4. Okay, that's smaller than 1, but that's between 0 and 1. But this is not an x. This is a negative x. So what do we do with negative exponents? What do negative exponents do to something? They take the reciprocal. So this is the same as 4 over 1 to the power of x. Now what is it? Now it's growth. Okay? All right. We're going to start graphing functions now. All right? Let's graph this first one. We're going to graph, basic 2 to the x. All right? We have to figure out asymptote and y-intercept first. So for asymptote, there isn't much to figure out. The default, which this one qualifies, is y equals 0. We're going to talk later about when that changes. So this is y equals 0. You just write that, that's it. Okay. Y-intercept. Y-intercept, you plug in 0 for x. So you say y equals 2 to the 0, which is, what's anything to the 0? 1. Okay? So the y-intercept is 0, 1. Okay. Now, to graph, you're going to pick points. All right? Is this growth or decay? Growth. Okay. So for growth, I like to pick these numbers, -1, 0, 1, 2. The thing with exponential functions, like we talked about, the numbers can get very large very quickly, right? This, I find, gives me some manageable numbers. But is this the law of the land? Is this like, are you like required by contract to only pick these numbers? No. Can there be functions where this actually is not a good set and you have to modify? Yes. You, the sophisticated pre-calc student, are going to figure that out, but we're going to learn along the way. Okay, so this is my standard. I pick when it's growth. So here's what we're going to do. 2 to the -1 is 1 over 2, so that's 1/2. 2 to the 0, we just did this, it's 1. 2 to the 1, 2. 2 to the 2, 4. Okay, let's go ahead and graph. Put in the asymptote first. Okay, so if I ask you to draw a bunny rabbit, even if you're like the worst artist in the world, like me, what is the one thing you want to make sure you have on your drawing? So like so it's a bunny rabbit. The ears, right? That's the asymptote for the exponential function. Okay? You cannot draw a bunny rabbit without the ears. You cannot draw an exponential function without the asymptote. All right? Yeah. Yeah. So I'm usually fairly good at seeing it, but what I like to do, just like I did here, just do it like a hairline above, right? And like we get it, we know. Okay, so we're gonna put in our points here. When x is -1, we're at 1/2, then 1, then 2, then 4, and now, okay, so the properties, the characteristics of exponential functions is they increase very, very rapidly, so make sure you go past all the dots and go up, and then you have to show me that this is following the horizontal asymptote on this end. It can, well, it does not cross, all right? Horizontal asymptotes can be, like a graph can cross a horizontal asymptote, but the exponential functions don't, all right? Okay. Next. So what's the domain? All real numbers. Okay, range. Is it above or below the asymptote? Above, so you start with the asymptote and you go up, since it's above. Okay? Okay. Limit as x approaches -infinity. What do you think? 0. As x approaches -infinity, it's 0. And here it's infinity. And it's continuous everywhere. Okay. All right. And look at that. You have just graphed your very first exponential function. Okay? Yay. I know that does deserve a pat on the back. This is like a big thing. Like exponential functions rule the world. Like everything in the world that happens is based on exponential functions. All right? Okay. What about this one? Growth or decay? This is decay. So what's the asymptote? Still y equals 0, because I haven't told you what changes it yet. Y-intercept, 3 to the -0, which is just 3 to the 0, which is 1. Okay, now, we're plugging in for decay. I like to shift to the left one, so I start from -2 and go to 1, all right? So, 3 to the -2 3 to the 2, 9. Invest a little bit of time to do this, okay? Not loads of time that you can't finish your test or quiz, but, you know, don't just ignore it either. So 3 to the 1. Okay, 3 to the 0 is 1. 3 to the negative 1 is how much? You guys know? 1/3. Okay, first thing you do, put on your asymptote. So, -2 is at 9, 3, 1, and 1/3. And there. Okay? Fabulous. All right. Domain. All real numbers. Range. It sits above the asymptote. So it starts at the asymptote and goes up. Okay. What's the end behavior as x approaches negative infinity? Positive infinity. And on the other side, 0. Where is it continuous? Everywhere. All right. So far so good, right? Okay. You remember the transformations, right? How to move a graph to the left, right, up, down. All of those follow the exponential functions. All follow all of those in exactly the same way. So, take a look here. This blue function is the original. It's 2 to the x. The red function is 2 to the x plus 1. Do you see how the plus 1 is added to the x? X is horizontal, so this moves horizontally 1 unit to the left. Okay? Just like all the other ones, a quadratic formula, the quadratic and L-bar and stuff. Okay. Take a look here. This is the original, 2 to the x, right? The blue one. Exponential growth, right? 2 to the negative x, this is a reflection around the what? The y-axis. Okay? And that makes it decay. So we graph it just like we would the decay. We actually graph one like that. Okay, take a look at what we have here. This is the original. What have we done here? Now there is a negative outside, right? Not with the x, outside the function. This is a reflection around the x-axis. And that's a question? Did you have a question? Oh, sorry, I thought you had raised your hand. Sorry. Okay? So this negative outside is a reflection around the x-axis. In all of these, did the asymptote change? Did the location of the asymptote change? It didn't, okay? The other transformation that's not here is a vertical translation, if you move it up or down. That's the only thing that will change the location of the asymptote, okay? All right, so let's do one. Okay, take a look here. You have 2 to the x, right? Is this growth or decay? Growth. Now you have x minus 1. What does the minus 1 do? Moves it to the right 1 unit. And what does the minus 3 do? Moves it down 3 units. Now, when the graph moves up or down, so does the asymptote. So, instead of y equals 0, now it's going to be y equals -3. Just that number exactly as it is. Okay? Now, y-intercept, same as before. Y equals 2 to the 0 minus 1 minus 3. y equals 2 to the minus 1 minus 3. What's 2 to the minus 1 these days? 1/2 minus 3. Okay, 1/2 minus 3. 2.5, but negative, right? So negative 5/2. So that's 0, negative 5/2. Okay. All right, so here. We're going to put in some values here. So look, if I put in a negative 2, this is going to be negative 2 minus 1, negative 3. I don't like 2 to the negative 3. It's like 1/8. That's not a good one, right? So here you have some, you can decide what to put in, right? So what if we put in a minus 1? 2 to the minus 1 minus 1 minus 3. So what's this? 2 to the minus 2 minus 3. How much is that? So 2 to the minus 2 is 1/4, right? Yes? No? Is everybody okay with that? Yeah. Why it's 1/4? Minus 3. So that's 1/4 minus 3. You have like 2 3/4 left. So it's negative 2.75. Okay. What if, okay, we'll talk more about that in a little bit. Okay, so what if I put in a 0? I just did that here, right? The 0, so that's negative 5/2. Okay, let's put in a 1. Two to the 0, that's 1. Okay, let's put in a 2. Oh, I'm sorry. Minus 2. When I put in a 2, what do I get? 2 to the 1 minus 3, negative 1. Okay, now, what if this first one gave you like some serious anxiety? Skip it. Put in another number down here. Go from 0, 1, 2, 3, right? I just said earlier, there is no law of the land, okay? All right, so at negative 1, it's at negative, okay, let's put in the asymptote first, negative 3. Jeremy, did you have a question?
I was just going to say, we need 4 points.
Yeah, 4 is good. Okay, so negative 2.75. And then negative 2.5, negative 2, and negative 1. Okay? Okay. Domain, all real numbers. Okay, does it sit on top or below the asymptote? Okay, so it's going to be from the asymptote, negative 3 to infinity. And as x approaches negative infinity, where is this function going? Negative 3, and then infinity. And it's continuous everywhere. All right? Okay. Let's do one more. Okay, so, all right, E. I'm not going to go into too many details of what E is, right? E is called the natural base, okay? This will all come together as we progress through the chapter. Most of the really real-world applications of exponential functions are based on that base, right? Instead of having 2 to the x or 3 to the x, most of the time we have this number e to the x. And you can go on for hours and hours over like where that comes from. But very briefly, in a lot of upper-level math or physics calculations, this term, comes up. And you have to look at what happens to this at infinity, and magically, this is like one of these black magic things in math, this levels off to some number 2.718, blah, blah, blah. We come to know that as E. All you need to know is E is this number. That's all you need to know. You should know that it's 2.718, just like you know that pi is 3.14, E is 2.718. But when you're using it in your calculator, you're always going to use the E button. You're never going to plug in 2.718. Knowing 2.718 is E, that's just to impress your friends. When you're doing the calculations, the E button. Okay? All right, let's do one. Okay, so what do you think? Growth or decay for this one? Growth. Okay. What's the asymptote? Y equals 0. Intercept. E to the 0, 1, 0, comma 1. Okay, so the asymptote is at y equals 0. Let's put in some numbers here. I'm gonna go with my standard here, because I'm gonna use the calculator anyway. So go ahead and take out your calculators. And before you do that, let's do some of the ones that we know, because it saves time and keystrokes. What's e to the 0? 1. What's e to the 1? 2.7. Now, when you're graphing, you don't have to go into any more decimal places than that, because can you graph the difference between 2.7 and 2.718? No. Okay, so for the other ones, go ahead and go on your calculators and find that lovely E button. It's on the left-hand column. Far left from the 1. Okay. So you're going to plug in e to the minus 1. And you know what? Okay, so calculator. Huh? No, just right here. So go over here. I want you to be able to use this one. So in the home screen, the E button is right here. Do you see that? So you're going to do e to the power of minus 1. Oh, look, it's 0.4. 0.4 is good enough. Okay? And what's e squared? 7.4. Fabulous. Okay, so go ahead and plug in those points into the graph, and you can sketch that graph. Okay. All right. So this is 7.4. So 0.4, 1, 2.7, 7.4. Do you see how no matter what the base is, the process is the same? Yeah. What's the domain? All real numbers. What's the range? Right. So these are your freebies, guys. Negative infinity, 0, and infinity. Okay? And it's continuous everywhere. Okay. One more, and then we'll stop. So these are all the same as we did before. One more, and then we'll stop. Okay. What do you think is happening here? So we have e to the 2x. What's this 3 doing? Moves it up. So what's the asymptote? Y equals 3. What am I going to do to get the y-intercept? Plug in 0. So e to the 0 plus 3, that's 4. So y-intercept is at 4. Huh?
Yeah.
Oh, sorry. I was actually thinking about something else. I want to modify this function a little bit. Because we haven't done a negative, a reflection yet. You know, it's okay. Let's leave it that way. Okay, so look at this right now. We're already at 3, right? If I plug in x equals like 2, this is going to be e to the 4. That's already going to be like a huge number. So for ones like this, because we're multiplying it by 2, I like to take numbers further from the negatives. All right? So why don't we go and say e to the, why don't we say negative 2? So here we're going to have e to the negative 4 plus 3. And you're going to plug that in your calculator. Okay, that gives you 3.01. All right, what if we have negative 1 next? E to the negative 2 plus 3. So I like to actually like recall the last one I put in and edit. I don't know, that's me. 3.1. 0, we just said was 4. 1, e squared plus 3. That's 10.4, right? So I think you can fill in, this part here. But when x is negative 2, we're at 3.01. Then slightly higher until we get to 4, and then it jumps up to 10.4. And I know 10.4 goes off the grid a little bit. If it's like something minor like that, it's okay. But otherwise, you should redraw your axes. Okay. Any questions on this? Okay. Here, what if you had this one? What if you had y equals e to the negative, what if you had y equals negative e to the x? Okay, y equals negative e to the x. I'm going to graph it right on here. So x, y. What would happen here? Yeah. For which one? I went up to the previous page. So look at the previous, I know I switched things on you. So look at this previous one, right? What if you had negative e to the x? What would happen? So y would be negative e to the negative 1, negative e to the 0, negative e to the 1, negative e to the 2. How does that compare to what we just did here? How are the numbers going to compare to what we just did here? They're just going to be the negatives, right? It's going to be negative 0.4, negative 1, negative 2.7, negative 7.4. So can you go ahead and graph those numbers here, right on top of this one? Go ahead and graph those numbers. Let's see how it looks. So this is the one I was modifying, right? The one on the previous page, e to the x. If you had a negative in front, all that would do is switch this, right? Flip it underneath. So The process wouldn't change. You just have a negative in the front of it. So what would the range be for the red one? Negative infinity to 0, because that's where the asymptote is, to the asymptote. Okay? All right, so we'll stop here for today. You have